Okay, so let's continue with this session. Our next speaker is going to be Massas. He's going to talk about choice-free individuality.
Yeah, and so I thanking the organizers for allowing me to be here today. I used to be a close neighbor of Chapman University for a couple of years, and so it's nice to be back. Yeah. Okay, so I'm going to start with a little bit of background about this project. So I think it's very well known in this audience that Stone's representation theorem for good algebras uses the wooden ideal theorem. And so also, of course, Stone duality relies on the fragment of the axiom of choice. Now, in point-free topology, there is kind of an analog of Stone duality, right? So the junction between the open set functor and the point functor restricts to a duality between Stone spaces and compact zero-dimensional frames. But that's actually a duality only under the prime ideal theorem. Otherwise, it's just an adjunction. But there is, however, completely choice-free duality that has been developed for well algebras, where on the geometric side you have actual topological spaces, and that's something that Nick Puznicki and Wes Hurley have done, and they introduced this class of topological spaces that they call UV spaces, and their approach has a lot of connections to something called possibility semantics in the semantics of classical and model logic. And also it has very strong ties to the torus hyperspace construction on the Stone space. And so one way that I like to think about this, the work is that it is in some sense a semi-empty approach, in the sense that so it is constructive, choice-free, but you do end up with spaces, like actual topological spaces in which you have some kind of points. But really, I mean, the best way to think about the points that you get in the spaces is as some kind of approximations of the classical points that you would get, assuming the axiom of choice. Okay, so that's the situation for closed algebras, and the setting that I'm actually interested in is a bit wider than this. And so in particular, so the starting point is this work by the Dutch mathematician Henrik de Vries, who generalized Stone duality to a duality between compact causal spaces and a class of algebras that, well, he didn't call them de Vries algebras, he called them complete contingent algebras. We call them de Vries algebras now. And those are essentially so complete good algebras with an extra relation that's usually called subordination relation. I'll say a bit more about this in a minute. And his representation theorem also uses the prime filter theorem in an essential prime ideal theorem. And now for compact causal spaces, there are many dualities, but in particular in point-free topology, there is also a very nice one due to ISBO, right, between compact causal spaces and compact regular frames. But this adjunction, right, restricts to duality actually only under the assumption of the prime ideal theorem. And so the goal, essentially, of this project that I was doing is to extend the semi-point-free approach of Wes and Nick to the Vries algebras to get a class of topological spaces that can be seen in some sense as some kind of like choice-free version of compact causal spaces. I'll talk a little bit more about the relationship between these spaces, which I call the Vries spaces, and compact causal spaces. And so, yeah, let me just say that this extension of this semi-point-free approach is kind of like a larger research program that I'm interested in, something that's sometimes called semi-constructive mathematics, which is supposed to be some kind of like middle ground between classical mathematics and constructive mathematics. You assume classical logic and the experimental set theory, but not the full power of the axiom of choice, just dependent choices. Okay, there's a little table there to kind of repeat what I said. Okay, so here's what I'm going to do. I'm going to start by talking about so the choice-free representation for de Vries algebras. Then I'll characterize the kind of spaces that you get in that way, and I call it de Vries spaces. Then I'll talk about the connection between so this work and point-free topology and the de Vries factor. And then, if I have some time left, I will talk about some applications of this. Okay, so let me start by finding what the Vries algebras are, So a contingent algebra is just a Boolean algebra with the relation, subordination relation on it. And so you can think of this relation as some kind of like strong order. I think the best intuition for them when I talk about is if you think about the elements in your Boolean algebra, some kind of like regions of space, then you want to think about the subordination relation as being something like being completely surrounded by, right? So A is completely surrounded by B, and that's how you interpret this subordination relation. And so you have some number of axioms that de Vries impose on that relation. So de Vries algebra is just a contingent algebra such that the Boolean component is actually complete Boolean algebra. And it is zero dimensional. Essentially, whenever B completely surrounds A, you can always kind of find region involved an element that sits in between the two and that completely surrounds itself. And this is essentially the way in which de Vries generalized stone duality, and this is going to be probably clearer in the next slide, right? So the canonical example of de Vries algebra is the regular open sets of a compact Hausdorff space. And there, so this relation is as kind of like a very intuitive interpretation, right? You say that B completely surrounds U if and only if the closure of U is contained in B. And if you think about this for a minute, then follows from this that if you have a cell space and not just a compact Hausdorff space, then the de Vries algebra that you get is actually zero dimensional. This encapsulates this idea of zero dimensionality of compact Hausdorff space. Okay, so de Vries showed that essentially, these are all the examples of de Vries algebras. Right? So every de Vries algebra is isomorphic to the regular open set of some compact Hausdorff space. And how do you construct the dual space of a de Vries algebra? Well, so de Vries introduced this notion of a concordant filter, right? So the idea is that you have this operation on, you can define those filters, and that's going to be kernel operators, like kind of like a closure operator, but not inflationary if you want. And then you just take the concordant filters are the fixed points of that operation. And de Vries was interested in the maximal concordant filters, which he called N's. And so how does the construction of the dual space work? Well, I think it's worth comparing this to stone duality, right? So the dual stone space of Boolean algebra, the way you do it is that you take the ultra filters of the Boolean algebra, which are the maximal filters, proper filters. And what de Vries did is that he took instead the ends of the de Vries algebra, so the maximal concordant filters. And this gives you kind of an idea of how you would want to go if you wanted to have some kind of choice-free representation of this, right? So clearly, the point that we should use the act of choice is in the maximality requirement. Use the prime ideal theorem to give you some kind of like maximal objects. And in fact, so in the work of Nick and Wes, where they define the choice-free dual space of a Boolean algebra, instead of taking the ultra filters, they take these filters. And so the natural thing you would want to do then is to take the set of concordant filters on a de Vries algebra instead of just a set of maximal concordant filters. And so that's what you do, and that's makes it work. And so the intuition here, I think, is that so you should think of the points in your dual space as being rather things like coarse approximations of the classical points, right? The maximal points. So you're only working with these approximations, and then you have some kind of order on them. So you order them, you have some kind of closest structure that's going to allow you to retrieve the algebraic structure that will otherwise be lost. Okay, so this is the definition of the dual filter space of a de Vries algebra. You just take the concordant filters, and then you define the usual stone-like topology on it. And then when you look at the specialization order that's induced by this topology, so it's very easy to see that it coincides with the inclusion ordering. And you're going to use this to model the subordination relation. And so you get something that's actually very close to what happens in the de Vries dual of a de Vries algebra. So you have that. So if you define that, in this case, so that V completely surrounds U, if and only if the closure of U is included in the downset of V, then what you get is actually representation of the de Vries algebra and the subordination relation by this term. Very, very standard. Okay. So that was for the choice-free representation theorem. And then let me say something about the kind of spaces that you get, which I call de Vries spaces. I need to introduce a little bit of notation here. So we're working with some kind of like ordered topological spaces, except that the order is actually exactly the specialization order induced by the topology. Right? So you don't have a lot of freedom, like say in Christian spaces, for example. And so I introduced this kind of like, so this down arrow to denote the closure operator on the upset topology, and the like up arrow to denote the interior. And so in this kind of work, we're interested in the regular open set, but regular open in the upset topology. So now I'm writing with this script. And so this is just a recap of these UV spaces, so the choice-free duals that Nick and Wes defined. So UV space is a space that is compact in T0, and you also want this, so these core sets which are compact open in the topology and then regular open in the upset topology. And you want those to be essentially Boolean algebra, so they are close on their intersection, and there is some kind of complementation that's given to you by the upset topology. And you want them to form a basis for your topology tau. And then you have a third condition, which is kind of a version of sobriety. You want that any filter on these row sets, you have a one-to-one correspondence between these filters and points in your space. And then so Wes and Nick showed that the core sets always in Boolean algebra, and the filter space of any Boolean algebra is a UV space. So these UV spaces are a certain kind of spectrum space. Okay. And so here is how I propose to generalize this kind of construction. So the key axiom that I have is this order normality. And so it's kind of a order version of the standard normality. So it's not exactly an obvious generalization, but it's close, right? So and this is essentially, you know, the only thing that you need, almost the only thing that you need to work. So if you have a topological space that's order normal, in the sense that I described here, and also such that its regular opens in the topology are also regular open in the upset topology, order regular open, then actually, if you look at the regular opens, they form the Brice algebra, and the subordination relation is given by same thing as before, right? So we say that V completely surrounds U, and only if the closure of U is included in the order closure of U. This downside thing is not the closure in the upset. Okay. And so this motivates the following definition. So the Brice space is a T0 compact and order normal, right? Then you also require that the regular opens are a basis for the topology, and you want them to be also order regular open. That essentially the first two axioms give you that this is, you're going to get into Brice algebra out of the regular opens. And then the third one is, again, so an uglier version of sobriety. So you want, essentially what you want is that the points in your space are in one-to-one correspondence with the concordant filters of the regular opens. Okay, and then so you can show that the dual filter space of any de Brice algebra is a de Brice space in a sense, and every de Brice space is homeomorphic to the dual space of its de Brice algebra of regular opens. That gives you pretty much all you need for the duality. So you need to do that. You just need to take care of morphisms. So morphisms in the Brice algebras are a bit complicated to work with because composition is actually not function composition, but you need to do something a little bit different. But on the side of spaces, it's actually pretty straightforward. So a de Brice map is kind of what you would expect in this kind of setting. So it has to be a continuous function, of course, and it also has to preserve the order in some kind of ways. And so this is what I call weakly dense maps. I think Angelis' talk yesterday was something like weak p-morphism, right? So it's the same kind of idea. So it's kind of like this weak way of preserving the order. Okay, and then so you can show pretty easily that the Brice morphisms give you DV maps, and DV maps give you Brice morphisms. So you get your duality between the Brice algebras and the Brice spaces. Again, so that's the choice. So yeah, I have some time to talk about the connection with point-free topology and the Torres functor. So let me do that now. Okay, so as I said before, right? So it's nice, very nice example for topology that you have that. So under the BPI, you have that the adjunction between frames and topological spaces restricts to a duality between compact Cantor spaces and compact regular frames. This theorem that I think is first attributed to Isbell. So that requires the prime ideal theorem, but you can also show purely constructively that the category of compact regular frames is actually equivalent to the category of degrees algebra. You don't need to have a choice because you're not going into compact Cantor spaces at any point. So how do you do that? Well, to go from degrees algebras to compact regular frames, you take the frame of something called round ideals, which are essentially dual notion to concordant filter. And to go from compact regular frames to degrees algebras, you take, that's very familiar, you take the Booleanization of your compact regular frame. And essentially the well-revealed relation is what you do. The Booleanization of what you would expect. Okay, and so I'm a bit fuzzy on the history on this, but I think so. The Booleanization was developed a long time ago by Massas first, but then I think it took some work by Buran, Bishvili, Nick's brother, to figure out that you could actually get this kind of equivalence between degrees algebras and compact regular frames. Okay, so I guess what you would want to do is to do the kind of same thing, where I have some kind of like choice-free equivalence between choice-free duality, I guess, between compact regular frames and degree spaces, and see how to get that concretely. And so it turns out that the kind of like the important notion here is this notion of an open set being well-rounded. So I mean, it's not terribly important to go over the details, but essentially the intuition is that an open set is well-rounded if this order normality axiom that I mentioned before holds for its complement. And so it's kind of like, I guess, kind of natural to work with. And what you can show is that this well-rounded open sets that are also order regular open, they actually are isomorphic to the round ideals of the degrees algebra of regular open sets. So that gives you a functor from degree spaces to compact regular frames. And if you want to go in the other direction, right, this is what's kind of interesting, you actually get something that's quite well known. It's a kind of Vietoris functor. So, I mean, there are a lot of like Vietoris functors laying around. So the one that I'm interested in is the one that goes from frames to spaces. Okay? And so the way this is defined is that you essentially take a frame, in this case a compact regular frame, and then you just delete the top element, and then you define on it this box topology. So if you've seen the Vietoris hyperspace construction for say compact causal spaces, what you do is that you take the non-empty closed set with the points, and then you define kind of like hit and miss topology. And well, if you want to do the upper Vietoris, then you forget about the miss parts of the diamond sets, and you just take the box sets. And that, so if you're doing with frames, then instead of having closed sets, you have open sets, so you can like dualize everything, but it's the same idea. And so then you can show that this construction always, it's not from a compact regular frame, this construction always gives you a DB space. And so that gives you essentially your functor going in the other direction. So you have an equivalence between compact regular frames and DB spaces. And so one part of this equivalence is given by this upper Vietoris functor. And so the consequence of this, if you assume the Boolean prime ideal, you can actually show that you can exactly understand the relationship between compact Hausdorff spaces and this degree space. Right? So every degree space is essentially the upper Vietoris hyperspace of a compact Hausdorff space. So, and this is similar to what's happening in the Boolean case, right? Where these UV spaces are called UV spaces because they are the upper Vietoris space of some spaces. Okay, so here's a confusing picture of what I just said before. So as you can see, we have this kind of like nice picture on the left in the realm of like Boolean algebras. And so what I did was essentially to show that you could generalize this into compact Hausdorff spaces and degree algebras. So do I have time for? Yeah.
Like more than 5 minutes.
Oh, okay.
Say 5 minutes.
Okay. So then I have time to talk about some applications of this in the short piece. So All right, so one thing that you can think about now is, so it's well known that Tikhonov-Stira, product of compact spaces is compact, relies on the prime ideal theorem. And in fact, Tikhonov-Stira for compact Hausdorff space is equivalent to the prime ideal theorem. Now, in point free topology, the co-product of the frame opens the family of compact Hausdorff spaces, compact regular frames if you want, that's going to be compact always, and you can prove that choice. But the problem is that maybe it's not spatial. If you don't have BPI. If you have BPI, then like easy duality is going to be spatial, but otherwise it may fail to be spatial. And so one thing you can do now is to actually define a compact topological space that you can think of as the choice-free product of a family of compact Hausdorff spaces. And so that's not going to be a compact Hausdorff space. That's going to be a DVS space. So it's going to be particular compact. And in fact, so if you assume BPI is going to be precisely the upper Editoris of the product of compact Hausdorff spaces. So that's one of the nice things you can do in a sensitivity choice-free setting. And then the second application that I want to briefly mention is this logic of compact Hausdorff spaces. So the Riz duality has been used by some people, some highly recommendable people, to show that. So they define a certain calculus, that, like a certain calculus that they call the symmetric strong implication calculus, and they kind of explain why for them this is kind of like supposed to be the logic of compact Hausdorff spaces. And essentially the idea is just that you extend propositional logic with, so it's a kind of model logic where you extend propositional logic with a strong implication connective that's essentially there to interpret the subordination relation. And well, so then you can show that this calculus is sounding complete with respect to compact Hausdorff spaces when you evaluate formulas as regular open sets. But of course, that proof of completeness uses the axiom of choice. And so what you can do is, if you don't want to use the axiom of choice, is to give a soundness and completeness proof for this calculus with respect to degree spaces. And so it works essentially the way you would expect it to. So the only difference essentially with the way you would evaluate this, so the way you give the semantics for this calculus in compact Hausdorff spaces is precisely in the clause for the implication, because your subordination relation is just a little bit different. Right? You use the order closure. And then what you get is that this logic of compact Hausdorff spaces is also sounding complete with respect to the classable degree spaces. Okay, and so yeah, so if you know anything about possibility semantics, you can kind of think of this as some kind of possibility semantics approach to kind of logics of region-based theories of space. Okay, thank you.
We have questions? Yes.
Yeah, so two quick questions. First, just to be clear on foundations, you're assuming DC and LEM. Is that right? All of these results?
Yeah, so experimental definitely, dependent choices doesn't play a role.
Okay, cool. So are you assuming any choice at all?
No.
Oh, very good. And then this strong implication that you just introduced, do you know, is it, in my mind, implications should be right adjoint to something. Do you know, is there some sort of strong product that this is the right adjoint to?
No, I mean, so this strong implication really, can we go back? Yeah, so the strong implication, right? So, well, if you want to think about it algebraically, so what you want is that it's either 0 or 1, right? And it's just there. So A strongly implies B. It can only be completely surrounded. Okay. Yes.
Okay, thank you.
So in the case of say upper Editoris spaces, when they characterize, like when Nicolas characterized the direct product of two Boolean algebras, take union of the two UV spaces and along with the union of the Cartesian product, right? And the topology is generated in the usual way. I would imagine the same is true of the degree space, or do you characterize this in the?
No, I mean, thinking about this. I think it would be essentially the same thing. I mean, so
Like in the case of ortho lattices, you have to incorporate that extra relation, right? Because you're working with like an ordered relational space, right? And so you need to incorporate the orthogonality relation and
Right.
nasty, but I would imagine with the degree
Yeah, no,
space,
yeah.
it's the same.
I see. So, yeah, so no, it's gonna be the same. You're not gonna have that problem here, essentially because of the order that you have, just coming from the topology, right?
Yeah.
So, yeah, I mean, you don't have to worry about that too much.
Yeah.
Are there any other questions also from home? You can unmute yourself and ask. Okay, so if not, let's start again.